In today's lecture, we're gonna talk about the statistical aspects that you need to consider when you're doing your data analysis. So the goals for the lecture is for you to learn how to use statistical aspects to interpret your data and to calculate parameters such as precision, absolute, which you calculate, using things like the absolute standard deviation, relative standard deviation. Sometimes they call it correlation of variance. It's exactly the same thing. Standard error, and all these, are methods, of calculating, dispersion. And dispersion, of course, refers to how your data is distributed around the mean, and that refers to precision, a very important figure of merit in analytical chemistry. We're also going to learn about confidence intervals, and that's essentially to know how far your data is from the true value, to know how the accuracy really of your data. I'm also going to introduce you to the t-test and the different applications of the t-test. And we're also going to talk about, the f-test, which is related to comparison of two data sets that have got different variances or different levels of dispersion. And then lastly, we're going to talk about what do you do if at all you suspect one data point or more data points are an outlier, and so they are far from the rest of the data. So do you just ignore them, or what statistical approach do you actually use to reject or keep data that you think is questionable? And that's what they're calling, what we call the Q-test. So in analytical chemistry, you are always, thinking about if at all I've got an analytical method, say glucose detection of blood using a glucose meter, which typically uses a technique called amperometry. Often you get varied readings, and so sometimes you're wondering, do we have a serious health issue? Is the technique that I'm using accurate, or the readings that are jumping all over the place, are they related, to a malfunction, of the pH meter and so on? Take a data set, like this, where you're analyzing blood sample for glucose detection, and you get, different types of data here. The average around 91.4. Just calculate, the dispersion, the standard deviation of this, and then you run a control sample. Now, a control sample, remember, sometimes I've been calling it the standard reference material, the SRM, which refers to something or a sample that you know very accurately what is in it. And I think in the last lecture, I tried to explain how typically you would get a standard reference material. Often you buy it, but the way the manufacturer knows the accurate concentration typically is by running that sample so many times and having other labs run that sample so many times using different techniques and using different technicians, to run it so that you make sure there is no error. And then when you average all that, you get a data, that is very close, to the true value. So I think we all know by now that all measurements, have got experimental uncertainty. The question, is how much experimental uncertainty is there? So error really is part of analytical chemistry. And so, like we talked about in the last lecture, you just need to quantify how much error, is present. Now, different analytical methods, have got different levels of uncertainty or different levels of precision. So depending on what you're analyzing, and the level of uncertainty that is allowable. You need to choose the right analytical technique, properly. I'll give you an example, and you guys are going to do this later on. Say you're trying to analyze a lead sample in water. You can use many different types of techniques. You can use titration. You can use atomic absorption spectrometer. You can use inductively coupled plasma mass spectrometry, and we're going to talk about this later. And all of them, have got very different levels of uncertainty. And so depending on how much uncertainty you really can allow, depending on what you're looking for, you can choose the analytical method, appropriately. Okay. So statistics, they give us the tools to accept conclusions that have got a high probability of being correct. And the statistics also gives us the tools to reject, conclusions that are likely, to be incorrect. Now, so often, the data, is distributed around the mean. And if everything is normal, you would find the data is normally, or using this so-called Gaussian distribution, is normally distributed, around the mean. So the peak, is actually almost always, symmetrical, and the mean, would be somewhere in between. I think all of us, know this equation, which this model, that we use to fit, any normal distribution types of data. Okay. Now, normal distribution curve, you normally get it if you analyze something so many times, maybe over 100 times. However, we know that's not practical, in the lab to do. Every analysis, costs money. It costs time. And so most likely, you can only analyze something probably 3 to 5, at best, to 7 times. But practically, normally we do it only 3 times. So we normally approximate the data that we are getting, to mimic the normal distribution. But in reality, it may not be the case, because we are only analyzing so few times, and so there's gonna be skews and so on, because you're only analyzing it so few times. And yet in a normal distribution curve, you normally get the data after analyzing it so many times. So when you're trying to fit in, a small data set into a normal distribution, remember, then it's a very hypothetical situation. It's an approximation, and it's all you can do. It's an approximation. So I think all of us know these critical, statistical methods of calculating things like the mean. I think it's fairly trivial. The mean is just an average, of your data set, so a summation of your data set, and then you divide that by the number of data sets, that you have. Now, as you increase the number of that data set, your mean becomes very, very close, to your mu, and the mu refers to the true value. All right, that's very, very close, to the true value. So again, you need to repeat something so many times to be very confident that the data you're getting is very close, to the true value. Of course, assuming you've done all your calibration and so on, such that you don't have systematic error, that we talked about. Now, the standard deviation, which we've talked a lot about, how to calculate that, is calculated as such. And remember, n, refers to the number of measurements, number of repeats. N minus 1 refers to the degrees of freedom. If you're talking about a population, and a population refers to when the n is more than, say, 30 different repeats, the degrees of freedom here becomes n. But normally in analytical chemistry, of course, we are dealing with very few repeats, maybe 5, maybe 10. And so the degrees of freedom is normally n minus 1. And so this is the absolute, standard deviation. Now, if you take the absolute standard deviation and you square it, normally we refer to that as variance. And as I've said up here before, as n increases, meaning as the number of repeats of measurement increases, the standard deviation here, approaches, sigma, which is a standard deviation of a population, okay? Now, standard deviation is used to calculate precision, and so you can use the absolute standard deviation, but another way of quantifying precision, very similar to absolute standard deviation, is where you use a so-called standard deviation of the mean, sometimes called the standard error. And so the standard error is calculated as absolute standard deviation divided by the root of n, and n of course is the number of repeats of the measurement. What's the importance of doing this? The importance of doing this is the following. The standard error, which is calculated as this, accounts for sample distribution, which is very, very important. You're accounting for how many times you have repeated the measurement. Another method, of calculating precision is, and we've talked about this before, is using the relative standard deviation. Remember, the relative standard deviation, doesn't have units. So you take the S here, the absolute standard deviation, divided by the mean or the average. And if you multiply that by 100, you call that percent relative standard deviation. You can equally multiply it by 1,000. And in that case, you're representing that data in parts per 1,000. So in most cases then, you've got this normal distribution. And ideally, for good, precise data, what do you guys think you want? A fat peak, or a very sharp peak? Now remember, if at all you've got a sharp peak, it means the deviation is very, very small. And that's a good thing, meaning that you've got better precision. So in analytical chemistry, we are always looking for a lean peak, a very sharp peak. We are not looking for fat peaks. Fat peaks are never a good thing in analytical chemistry. So maybe one other thing to mention, familiarize yourself with using Excel spreadsheets, to do the calculations, the statistical calculations, because that's what you're going to be using, especially, in the labs. Now, another way sometimes of representing these normal distribution curves, is by calculating, the area under the peak. And sometimes, it's been fairly well defined relationship, between the area under the peak, where you take, say, the average, which is the mu in this case, is the true value, meaning you've done it many, many times, plus minus one sigma, is equals to 28.3, okay, percent, of that peak. On the other hand, mu plus minus, 2 sigma, that's the standard deviation, encompasses, up to 95, percent as the area under that peak. And mu plus minus 3 sigma entails nearly 100%, the area under that peak. And so if at all you're looking, for the confidence level or the confidence interval, or where my true value, lies, and that's the purpose of doing confidence intervals. Sometimes, we use, these plus minus 1 sigma and so forth. Now remember, life is not always normal. In fact, in most cases, it's not. And you would expect, in some cases, for the mean to be equals to the median. Okay. Now, that is only true if at all you're dealing with a normal distribution type of data. But in reality, because again, like I said, you don't repeat the measurements too many times because of the the constraints of time, of money, and so forth. In some cases, you may actually get data, that has got a poor distribution, meaning it's not symmetrical. And so in the event that you get a data set where the distribution or the standard deviation is high, meaning the peak, is generally skewed, then in that case, instead of reporting the mean, report the median. Okay? But for a normal distribution, typically the median, is equals to the mean. So let's talk about how do you predict, how close your value, your experimental value is to the true value. How do you predict, how accurate, your measurement is? So you use this confidence interval relationship, where you got the mu, that's your true value. You've got your x bar, which is your experimentally determined value, plus minus, what they call the student's t. And the student's t, was actually a data set that was developed, in 1908, by this gentleman called Gossett. But because he was restricted to publish his work, for proprietary reasons, they called, the student, they called him, the student, so the name was not actually used. So the T, in this case, is a set of data set, with fairly well experimentally determined constants at each individual confidence interval. And so that one you get it from the table. And S, on the other hand, of course, is the standard deviation, and the root of n here, n refers to the number of repeats. Now remember, and I think I've already talked about this, the ratio of the absolute standard deviation to the root of n, sometimes we call it, the standard error. And so this confidence interval relationship, you can say it's mu is equals to the x bar plus minus, the t, the student's t, multiplied by the standard error. Okay. And we use it again, to approximate, how far my experimental data is to the true value. In fact, in the industry, if you end up, in a manufacturing industry, you're going to use it in form of a control chart. And so you've got a situation like this, where you've got the true value, your data set should be very, very close, to a determined, value, experimentally determined value. So if at all you're doing, say, synthesis of a pharmaceutical product, the pharmaceutical product, say aspirin, the company wants to have, say, 2.00 milligrams, of aspirin in that tablet. So that's going to be your mu value. But for every batch, that you produce, there's always a bit of variability. So in one case, it's going to be 2.01 milligrams. In another case, maybe less, 1.99 milligrams. And so the companies often, make this control chart where you've got, say, the mu, that's a true value, the expected value, but in reality, you never get exact that. And the products, that end up in the market are distributed very, very close, to the true value. How close? Often very close to the 2 mu plus, say, plus minus 2 sigma to the root of n. Sometimes they call that, the upper warning line. Meaning if at all you've got data, that is too far, away from these 2 sigma, then in that case, you have to there's a problem in the company and that is not acceptable. It's too far, from the true value from the expected value. So you can see, this confidence interval is what they actually use, when they are creating the control charts for quality control, of manufacturing, whether it's pharmaceutical companies, whether it's making beer in breweries, and so forth. So very, very common, kind of statistical platform, that we use for quality control, which is where some of you are gonna end up. As you've seen, the student's T here, it's a table. And the student's T, as I've mentioned, is dependent on the confidence interval or the confidence level, that is expected or that you want to use to calculate. And the degrees of freedom, the n minus 1, that's the degrees of freedom. So if at all I give you a problem like this, then, calculate at 95% confidence interval. A data set that looks like this. You are running, say, sulfates in water. You've done 6 different measurements, maybe using a titration. And that is your standard deviation, that is your mean. Now, the student's T, as I've said before, you've got 6 measurements, so 6 minus 1, it's 5 degrees of freedom. So you come here and look at, you're expected to calculate or to determine the student's T at 95% confidence, and there are 6 measurements, but the degrees of freedom is n minus 1, so it's 5, and so the T from the table is 2.571. And so that's a T, in the table. And then after that, I can just simply substitute, those numbers into my confidence interval equation. The X bar, that's the mean. The T is what I got from the table. And I've got my standard deviation. It's already determined. And then the root of n, the number of measurements are equals to 6. And so you can see now my mu, or my true value, essentially I'm saying should lie, within this range at 95% confidence level. Okay? And so typically that's how you determine how far, your experimental value is, from the true value. Where does the true value lie? And so just to summarize, some of the factors, that affect the confidence interval, and I think it's fairly straightforward from this relationship, would be the number of measurements. How many times have you repeated, the measurements? The more you repeat the measurements, the more confident you are, that your true value, lies within a fairly narrow range. Now, you're also going to see that beyond, say, 15 measurements or so, the T value, keeps getting smaller and smaller. Meaning, if at all you've got only very few measurements, your T, your T value is actually fairly large. And so in that case, your confidence interval, is bigger because you're not very, very confident. If you repeat the number of measurements many, many times, your confidence interval, tends to be thinner, which is what you really want. And the other factor, that affects, of course, the confidence interval would be the level of confidence, that is required. And so in most cases, most people tend to use 95%, confidence level. But the more confident you want to be, then the bigger the range, as you can see, the more confident that you want to be, the T, becomes a lot bigger. And so in that case, the range, becomes a lot bigger. So in the next lecture, I'm going to talk about, the other applications of the student's T, the T table, other than, just using it, for the confidence interval calculations. So the other applications of the student's T, other than the confidence interval application. and I'm gonna talk about them in the next lecture.